gentlemen, any questions? Well, then I will demonstrate the need for questions. So let's say that we want to do the homework assignment with this subsequence. So we want to make it so that L is S is a subsequence of adjacent elements in L. So how do you do it without recursion?
So I broke the original list into two separate pieces and appended them differently.
Okay. So let me draw the picture that will be helpful here.
So the original list isn't particularly useful as a whole at first, but if I were to take the first part and just S, then I can use append to generate the list.
Yes, so I'm just going to give this one a name, A, and the one here I call it B.
Yeah.
And then I'm going to call this one C. And now we're done, right? Because now I can read off what the relationships are. I can append A and S together and get C, and I can append C and B together and get F.
Yep.
Okay? So anything like that, you should be able to recognize and do in 15 seconds or less if you want to call yourself a competent programmer. Right? So this is a situation that occurs surprisingly frequently, and that's the first thing you always want to check. Can you just do it with a pen? In fact, I was a knucklehead when I did this, and I wrote not last without using a pen. And I wasted an entire minute writing it with recursion when I could have said so not last is supposed to be all but the last element.
So then you just
and so that means if I append so X is the list. And now I have append a list with one element, and then I get S. Okay? So let me take these away because you're supposed to think through yourself. So the first thing is try to see whether append can solve your problem. Because append is always easy. Well, append can always solve your problem. Like when you go to the sub-list feature here, append by itself is not going to be really useful because when you look, for example, at the sub-list containing 1 and 3, how is append going to find it in here?
can't.
So in that case, you say, fine, append is not going to work out. So let's look at subsequence again, and let's say that we didn't have the bright idea with append. You can always use recursion, right? And so Now, we need to make a choice. What do we want to recurse on? The first one or the second one? So recursion means, we're saying this is a head or tail, or we're saying this one here is a head and a tail, and then hopefully we can do something with the tail. Pick one.
Idea where like the orders are A, and B, and A is a prefix of B, or A is a prefix of the tail of B.
Okay, so
tail is a subsequence of the tail.
So we have S and L here. So are you trying to recurse on S, or are you trying to recurse on L?
Not sure what that means.
I recurse on L.
Well, recursing on, it means that one of the two you're going to be writing out as head and tail.
Yeah.
And then you match, then you try to do something with the tail.
I had to row it. So I think the second argument has to be right as head and tail.
Okay, so you want to write the second argument as the head and the tail. So let's go with that. So we say this one is an S, and this one has a head and a tail. And then we want to say that's true provided something.
True provided prefix, S is a prefix, H const T.
Well, let's do this one. So let's draw the picture. So we have my tile is L has a head, and then it has a tail. And now S is sitting in there somewhere, right? Like this. So it seems to make, in this case, isn't S a subsequence of the tail?
Yeah.
Yeah, it's sitting in here. That's what subsequence means, right? So that seems fruitful. So it's undoubtedly true, so maybe it'll be helpful, right? Now, there might be another case that would be useful where it's not a subsequence of the tail, but where it's like sitting here. That would be a case that's not captured by the first picture, right? So, how would we write that one now? In this case here, when we look at S, what can we say about S?
It's a prefix.
Let's do the easy thing first. What's the easy thing that we can observe about S?
It's a list, so you can split it up in head and tail.
Yeah, you can always split it up in its head and tail. And. Thank you. S has headings, right? That's what we know in this case. So we have subsequence. So S has head H. And some tail that I'll call T1 or T2. And then the other list was H and T. Provided that. So now let me write S as H and T2. And now we're coming to your thing with a prefix. Look at the picture. What's the prefix of what?
first list, prefix of the second list.
Okay. T2 is a prefix of T, right?
Yeah.
When you look at the picture, and you say, okay, this whole thing is sitting in here, supposedly, T2 is a prefix of T. T starts with T2.
It's going to keep going through the same case.
Well, we're not going to keep going to anything, we're just going to write this amazing fact down. So, how do you write down that T2 is a prefix of T?
Why can't you just use recursion?
I'm not going to use recursion if I have an easier way.
A prefix T2T.
Yeah, but what if you don't know what prefix? There actually is a built-in predicate called prefix, but we can do this with what we know.
What, and or something?
Thank you. With a pen, right? So, do it with a pen.
Then T2 and some certain list would create T.
T2 something T. Yep. There you go.
Yeah.
Okay.
You can just say append SL, right? Because S is a prefix of L. You don't even need to
Probably
spell it.
could.
Yeah, that's what I did.
I probably could, yes. So, I buy that. Then I don't even have to do any of this stuff.
Yeah, I thought we were doing that because you didn't want to use a pen.
Okay, oh, I see. No, so I think Tyler's much better idea and say, I don't have to split up the H and G. I can just say append SL. Yes?
Why is it necessary to provide another predicate just for the empty list?
That's a very good question. I was about to ask, when does the recursion stop? Which is probably kind of saying the same thing.
Yeah.
And so if you implement recursion, you would now naturally say, how do you make the base case for the recursion? What would be the base case?
Empty list is a subsequence of empty list.
Yeah, the empty list is a subsequence of the empty list.
That's already cut. That's redundant.
Now what you say is that, if you do it this way, you have to have that case. If you do it Tyler's much better way, where you don't do the split up here, then you don't have to have that because that's a consequence of his prefix then.
So why is it still necessary if you're doing the double append technique, the first one you showed?
Then it's not necessary.
It's not.
No. With a double append, that's a single line. Try it out.
But you need to say that on the second or on the first rule, you need to say that the S cannot be equal to the empty list. Because then you're going to get repeats.
Oh, I see.
Because then your first case is, your second case is going to catch empty lists.
So let's see. So you say in this case here, I have to say that S is not empty.
Yeah. After you do the subsequence call. Because if not, you're going to get like a redundancy. I don't know.
Oh, you get an infinite recursion otherwise. No?
No, you just get a redundancy.
We get a redundancy,
You get a bunch
okay.
of empty lists.
Oh, I see. Yes, so that's very possible. Yes, so now, what you now see is like the starting point, and now you can start fine-tuning the thing. Do you need to force a list not to be empty? How would you force a list not to be empty?
Comma S backwards slash equals empty.
Yeah, that's ugly. You can do that, but it's much easier. You can force any list to be non-empty by writing it with a head. Right, if you write S, in this case, you could say it has the form H1 vertical bar underscore. All right, so that's kind of the basic, these are the basic two tools that you have to deal with the SOMA. That you can recurse and you can use append. And everything in here you can do with those two techniques. All right, now any questions?
Oh yeah. I ran into an issue in my permutation. My implementation allows you to do an array and then a variable, but if you do a variable then an array, it goes in infinite recursion. Do you want us to support that?
So, no.
Okay.
No, you don't have to do that. That's harder to do.
Okay.
Yeah, I made a note to myself that would be a nice improvement, but I have the same limit that for permutation, the left list has to be supplied. It makes sense that the other thing should work.
Right. Like logically.
But, and I'm sure I could do it if I put in some time in it, but I didn't do that. All right, that's the homework. So today we want to talk about how Prolog actually works. And one reason to talk about it is that I've had a few comments on Piazza where people say, should I use recursion, should I use a loop or something like that? And we are thinking about a recursive approach when we solve problems, or we're thinking about looping, but the truth is Prolog has no idea what recursion is or what looping is. Those are not built into Prolog in any way at all. So if you think about SL1, what does SL1 know? SL1 really knows only one thing, and that is how to make function calls. SL1 didn't know anything about recursion in particular, except the function could call itself. And so we kind of got recursion because we had function calls. Prolog knows nothing about function calls. There's nothing in Prolog that would say, here is a function call. Imperative languages know about looping and variables. You have mutable variables. Prolog doesn't have any of those features either. So let's see what Prolog does do. So let's look informally at something. Let's say that I have the member predicate defined, as you've seen on the first day of Prolog, no, on the second day. And let's say that I have a goal, namely to compute whether Mary is a member of John, Mary, and Pat. So here's what Prolog does. It says, I need to do something with member. I'm going to look at all of the rules that I have that start with member. I'm going to apply them in turn. So let's do the first one. So now I have this head, meaning the thing to the left of the colon equal, and I have this goal. Now I'm going to do what's called unification. I'm going to try to find a unifying assignment of the variables that are floating around. And so what's it going to do? It's going to do the only thing that it knows how to do. It's going to say, okay, Mary is supposed to be X, and John, Mary, Pat is supposed to be X, something else. So if Mary is going to be X, then it knows that X has to be Mary. If John, Mary, Pat has to be X and the vertical bar, then it's going to match those in turn. It says, okay, John has to be X, and the vertical bar has to be the tail, Mary, Pat. And now it's going to fail, because X can't simultaneously be Mary and John. So it's going to move on to the next choice. The next choice is this one here. It's only going to look at the head, and again, it's going to try to find a unifying variable assignment. So now we want to unify member X underscore T with this thing here. And this one is going to succeed. It's going to say, well, X can be Mary, underscore can be John, and this T here can be the list consisting of Mary and Pat. So that's our unifying substitution here. Now it says, fine, I've gotten into this. I'm now going to look at what's on the right-hand side. What is on the right-hand side? It's some comma-separated list of clauses. It's going to look at, of terms, I should say. So it's going to look at each of the terms in turn. We only have one. And now it's going to do the exact same thing that it did before. It's now going to say, well, before I wanted to prove this thing. Now I'm going to focus on proving this thing with the substitutions that I have, namely X is Mary, underscore is John, and T is Mary Pat. So it's now going to make a new goal, and say, yeah, that's the one that I'm now going to focus on. So we started with a goal, and we've now moved on to a simpler goal. That's our goal now. And how is it going to do this goal? Exactly the same way. It is going to say, well, it starts with member. Let's see all of the things that I could use with member. There's two, this one and this one. It's going to start with the first one. It's going to unify member X, and this thing here, with member Mary, Pat. Now, how's it going to do that? It's going to say, well, the first argument has to match, so X equals Mary. The second has to match, so X and the underscore has to do Mary and Pat. This now works, because now X can be Mary and underscore can be Pat, and we've managed to make them match. So Prolog's going to say, true. It has found the way to true. So now it knows that this one here is true. There's no others on the right-hand side. And so now it knows that this one is true, meaning this one here with this variable assignment. And so that's what it does. So it does nothing more than looking at so whenever it has a goal, then it looks at the name of the thing. It finds all of the rules that have that name. For each of them, it looks at the head. It makes a variable substitution. It plugs that into all of the things that it finds on the right, and it turns them all into goals. So let's look more in detail how it does what's called the unification. So we're given two terms, like, let's think of how this kicked off. We had this term, and we had this term. And what do we want? We want to have the definitions for variables that make the two terms identical. So in this case, we wanted to have some assignment for the x's and so on. So here I have the positive example where it's going to work out. So I have the term member of x and something, and I have a member of Mary in this. And so our solution is we look at all of the variables that could occur on the left and the right. In general, they can occur both on the left and on the right. And we want to assign them something so that when I plug in the assignments on the left and I plug in the assignments on the right, that I get the exact same literal term. And I mean the exact same literal term. There's no computation, there's no function calls, there's no simplification. It has to be 100% literally the same term. Okay? So how do we do this in general? There's an algorithm that I'll show you in the next slide called unification that takes as its input two terms, and as it outputs gives you a list of variable assignments that is the most general variable assignment that it can come up with that makes the two terms identical, or it gives up and tells you that it fails, it can't make such an assignment. So here's the algorithm. And we start out with a pair of terms where we say we want the left side and the right side to be the same. So here's the starting pair. This one here, I want it to equal this one. I write these pairs of the form L equals R, where the equals doesn't mean that they are right. The equals is wishful thinking. I want them to be right. So that's how I write each pair. So I started with a pair of terms, and as I progress, I get more and more of these pairs. I'll throw some out, I toss some others in. And when I'm done, one of two things will happen. Either I get a whole bunch of pairs that say x equals this, y equals that, underscore equals that, and that's my successful variable assignment, or I fail. So here's how the algorithm works. You have a set of these pairs, and you choose the first one on the list that you can work, and do the associated action. So there are 6 cases. Let's say that you find an equation that has the same functor on the left and on the right, and it has the same number of variables. In that case, you throw out this equation and you replace it with n equations where you say each of the arguments should be the same. Now you have more equations, but they're simpler. Let's say you find 2 functors So you find an equation where you have an f on the left and a g on the right that are different. In that case, you give up in disgust. You say, I can't ever match these. Let's say you find, and these are the two cases where you don't have any variables involved. Now we're looking at the case where there's some variables. Let's say that you have the case x equals x. You just throw it out. It could happen sometimes. Let's say you have a term on the left that's not a variable, and you have a variable on the right. Then you just turn it around so that you have the variable on the left. At this point, any variables must be on the left-hand side, and you're not going to have an identity. So now you're going to have a term that has the form x equals t. So eventually all of the terms will look like that, because if there had been anything else, you would have broken them down into something that has variables. Remember, anytime that you add a term that involves two things that are not variables, you can apply rule 1, where the functors were the same, and then you can just equal the arguments, or you can say, well, they're not the same, and so the whole thing is not working out. So now everything has the form variable on the left and some term on the right. Now, if you have this term on the right and the x doesn't occur on the right, which is the happy case, then what you do is you apply the substitution to all the other terms and you throw it out. If you have a situation where x equals a term and that term also contains x in some way, then you halt with failure. When you're done, you're going to have the situation where all equations have the form x equals some term, and the x doesn't occur anywhere else. So let's try that out with an example. So here is my initial pair. This is the initial equation that I want to solve. I'm going to write the brackets here as cons so that it's completely uniform. So I'm writing the underscore vertical t as cons, and I even introduce a new variable here so that the underscore doesn't look special. So now let's see what we have. On the left we have a term that's made up out of smaller terms and variables. On the right we have a term that's made out of smaller terms and variables. That is the input to the unification algorithm. So let's see which rule can we apply. Can we apply rule number 1? Sure we can, because it says some term equals some other term. Some term equals some other term. They both start with member. That's good. So we don't fail right away. If they had different names, we would have failed. So we now get two equations, namely x equals Mary and cons zt equals cons of John, cons Mary, John's blah blah blah. So these are these two equations that we have now. We started with one equation, and we got two equations. Maybe that doesn't sound like a good trade-off, but these equations are simpler, and by breaking them down, we will eventually get them. Now this one here, there's nothing else we can do with it, and so we're leaving it alone. Why do I say that? Because the x doesn't occur anywhere else, so we're not benefiting from substituting it in, and there's no x on the right-hand side, so we can't give up. So this one here is done, it'll never go away. This one here we can further simplify. Why? Because we have a term on the left and a term on the right. We have a rule for a term on the left and a term on the right that says as long as the term matches, which it does, it's a cons here and a cons there, make a new equation for each parameter. So the first equation is z equals John. That's the one here. The second equation is t equals cons Mary, cons Pat. No, that's what we have here. And now we're done. We can't do anything more with these. And look what we found. We found a solution for x, y, and z, or to x, y, and t, I'm sorry, so that the left hand and the right hand side are the same. That's exactly what we wanted. We have done that by following the stupidest possible algorithm that you can to solve these equations. In these equations, we know nothing about what member means, what cons means, what Mary and Pat mean. We just treat them as abstract symbols and say, well, if these things can't be the same, what is the lowest common denominator meaning of when they are the same? And by using this algorithm that you would have invented in 5 minutes if you had to write down how you match these, we have solved this variable substitution. This is the only non-trivial thing that Prolog does, and it's not very non-trivial. Right? So, let's now look at the other two parts that go into Prolog. The first one is the stacking up of goals. So, Prolog keeps a stack of the goals that it needs to work on to prove something. When you start out with a query, then that initial query gets pushed on the stack. So let's say we have a bunch of I highlighted the wrong thing. This is the query. So let's say we have a bunch of clauses, our parent and grandparent stuff, and now I want to solve this query. Who are the grandchildren of James I? So this here is the top of the stack. I only have one thing on the stack right now. So now I'm going to pop it off and say, I'm going to solve the sucker. What do I do? Well, I need to find out what are the matching rules. There's only one. I need to do unification. I unify this thing here with a head. That gives me a unifying substitution. In this case, we can just read it off. The substitution is x equals James I and y equals g. I now apply that substitution to all of the things on the right-hand side. And so when I do that, then x is James I and y is g. Then I get two clauses, parent of James I and z, and parents of zg. Now I take both of those right-hand sides and push them on the stack, but I push going in a reverse order so that I pop off the leftmost one first. That way the leftmost one gets executed more quickly. And so what you in effect get is a depth-first search. Because in the end, this parent here may push other things on the stack, and the very first thing that it pushes gets popped off and gets solved. And so you get the smaller goals done first. That's what depth first means. So that's how this pushing stuff works. And now let's see what we're doing. Now I pop off the top of the stack, and I need to solve it. That's my goal. How do I solve it? Well, I look for parent. I try to unify with this thing. Can I do it? Yes, because James I equals James I. That is true and gets thrown out. There are no arguments. Charles I equals Z gets turned into Z equals Charles I. And that's my unifying substitution. So now I pop off the goal because I'm done with it. I apply the substitution to the rest. And so the Z becomes Charles I. And now I need to prove this thing here. And eventually, I will get solutions for G. Now, doing all these substitutions at all times is a little bit tedious, so it doesn't actually do the substitutions. Instead, it keeps a list of the substitutions and the goals are the original terms. So when you trace through the graphical tracer that you saw a couple of lectures ago, then you will see the original substitutions and, the original terms and the list of substitutions. So that's what it does. It keeps a stack of the goals that it still feels the need to prove. Every time that it gets into the left-hand side and has a unification, then it pushes all the right-hand sides onto that stack. So that stack will grow whenever you have more than one right-hand side, and it'll shrink whenever one was able to prove something. So none of this is really rocket science. This is what you would do if you had to test these rules. You would say, well, if I have to prove them all, I prove them one at a time, and the stack is just the way to do this. Now there's a third thing that Prolog does, and that is that it takes care of all the choices. So let's say that I want to solve the goal parent Charles I and G, so I want to find the children of Charles I. There are 4 choices, never mind the 5, that's a typo. So in my set. Now the first one here, well, let's see what happens. Can I unify parent Charles I G with parent James I Charles I? No, because the parent match, and then it's going to come up with the equation Charles 1 equals James 1, and G equals Charles 1. And Charles 1 equals James 1 is going to fail because that is this case here. Charles 1 and James 1 are both functions with no parameters, but the functions have different names. So now we're saying, okay, that failed, and now we have a more interesting situation, namely that here there's 3 matching clauses. Right, they will all work out, and Prolog will try them all. And so the way that I think about it is that it says, okay, so I have multiple choices, and I mean realistically it has the multiple choices at this point. I've just ran ahead and said this one is not working. So really the way it thinks about it is it has 4 choices at this point, and it's going to say, I'm going to try them one at a time. So you can think of it as now making 4 copies of the stack and running each of them separately. Or you can think of it as saying, I'm just going to make a copy of the stack, and then later I backtrack and try the second choice and so on. People tend to think about the backtracking way. So now we're stashing away a copy of the goal stack. We now, because we had a successful unification here, we push the new goal on the copy of the goal stack or the original, I don't care. And we just run through all of that thing until that goal stack is empty or it fails. And then we're coming back to the next choice point and do the same thing. Make a copy, push it on that, and so on. And so that way we're going to be backtracking to each of those. So every time that there is a multiple matching heads, then this backtracking happens. Now you've seen absolutely everything that Prolog does. It doesn't do any more than that. So it does 3 things. Unification, this thing here, that stacking up these multiple goals whenever it sees commas, and backtracking to all the choice points whenever it has more than one matching head. Well, okay, there's one more technical thing. Sometimes you have to worry about variable renaming. So look at this case here, that I have this query about ancestors, where I say x is an ancestor of z if x is a parent of y and y is an ancestor of z, or if it's a direct parent. And now I issue the following query and say, I want to know what are all the descendants of James I. So I just naively issue it as ancestor James 1 and x. And so now notice that there are 2 different x's. There's the x that comes in here, and there's the x that comes in here. And obviously you have to do something about that because they're not the same x. And so what you have to do is when you say, okay, I want to solve this thing equals that, before embarking on that, you have to look at the variables on the left and the right and rename some of them so that they don't clash. So here I've renamed the one in here as x1, and then that works. And that's really all that there is to it. So now my unifying substitution is solved as this, and then I apply it. And so all you have to do good housekeeping with these variable names. So that really is all that Prolog does: unification, the goal stack, and the backtracking to the various choice points. And so it is interesting that it doesn't do any of the things that you normally think about what programming languages do. It doesn't have any function calls. Right? There's nothing in there that says this is a function call. It doesn't do any loops or jumps or assignments, mutable assignments. And yet anything that you can compute in Prolog. So it is a universal programming language. All right, so in the lab, I want you to do this in slow motion. So I want you to actually figure out the unification in a particular example, and to follow the rules absolutely exactly to the dot, and write down what you did. So these rules here. So I don't want you to have an intuitive understanding of what it does, but I want you to blindly and slavishly apply the algorithm. The second thing is, I thought it would be nice to be able to trace through this in a way that's a little bit different from the tracer that you've seen. So I found a Scala implementation of like the simplest Prolog that you can imagine. It's 200 some lines of Prolog, and I've put in a thing with trace messages in there, and so that you can go and trace them. All right, so let's do that, and then we'll regroup in 20 minutes or so and talk about it. So it says, consider these two terms and compute a unifying substitution. So what we do is I just type it out here so we can have a record of it. So I have this is my initial equation. And now I'll go to the algorithm and follow along. So I only have one equation. I need to match one of these 6 steps. Well, clearly it's the first one grips, right? Because because I have member here and member here, so I have the same functor on both sides. So let's go for it. So I now make an equation for each of the arguments. So x equals x17 is one of them, and the other one is cons. I'll just copy and paste it. Equals this one here. Okay. So now I pick one of the rules, and I can just deal with the first one. It says x equals x17. So that is this case here, x equals t, where x does not occur in t, and it occurs elsewhere. T is the right-hand side, doesn't occur there. And does x occur elsewhere? Not really. What I'm actually going to do is, because I want to grip it the other way around, I'm going to turn it around and say it says x17 equals x, because then the x17 does occur elsewhere. And then I copy the other one. Okay, now I can do the substitution. And substitute it back in here. So I put just an x in, and I'm rid of one of them. So that's good. Now I only have one term, and I apply again rule number 1. And set the arguments to each other. So I have John equals x, and cons Mary Mill equals t. Now I flip the 2 around by rule number 4. And I'm done. Okay? Okay, so that's the solution, and so I just mechanically follow these rules, and I get it up. So then it says I'm supposed to do something else. Hang on. Okay. And now it says apply the substitution to the body of the clause. Yeah, that's step 3. Okay, so let's see. Where's
Where were we on step?
what's that?
I thought we just finished step 1.
Oh,
I thought we're on 2.
oh yeah, you're right. You're right. Okay. All right. Okay, now let's do 2. Thanks. So we're supposed to do this thing here, and equals, as I unify with the head of the clause. But of course now I have to be very careful doing that. I have to rename this one of the x's, so I'll rename this one here as, let's rename it to x17, because then I can do what I've just done. Okay, now the unifying substitution is exactly what I just did, right? So it's the one over here. And now, so that's step 2. And now in step 3, I apply it to the body of the clause. So this is the head of the clause, this is the body of the clause, and so when I apply the substitution, then I get John and Con's Mary Nil here. So that's what I get, and that'll of course then be my next goal, which will fail, but whatever. So again, appreciate just how completely mechanical all of this is. I have a goal, I have a clause, and now you follow a recipe. You say, I unify the goal and the head of the clause. I get a substitution. I apply the substitution to all of the things that come after the colon minus. It's completely mechanical. There's no thinking or anything involved, right? It just follows this algorithm. All right, so the other thing is when we run through this little program here to see the traces. So first of all, note how nifty this is in Scala, where they actually overloaded the colon minus, and they overloaded the question mark to be a query, and they couldn't overload the dot. The dot is not one of the overloadable operators, so they did the next best thing that they could and used the exclamation mark. But whatever. And so then they have these calls to more that look like exactly like what you do when you type it in Prolog. So they try to really mimic this. And then over here you see the algorithm. I didn't particularly study all of the algorithm, but we can see where they did the unification. So here they unify some lists of terms, and here they unify a single term, and where they have some incoming substitution, and then they get out an iterator of substitution. So that's, I don't know why they made it as an iterator. I should really change that so that it's a list and that we can see it. The iterator, you can't see it without destroying it, which I didn't really like. But I just found this thing and wanted to make use of it. So here's then the output. So we see that it finds the need to unify x1 with x. So let's see what's the computation that we're running. So we're having as our goal this thing here. Okay? So what's it going to do to try to achieve this goal? It finds the matching rules, those are these two. So it tries this one first. Why does it want to unify x1 with x? So yes, so first of all, somewhere it must have done some renaming. Right, so one of these x's must have been renamed into x1. And then it must be at the phase where it is trying, where it already identified these two. And so it's now matching this x against that x, except it's renamed one of them. The next thing it wants to unify is x1 colon colon x2's with John, Mary, Nell. This is x1, x2's, and this is John, Mary, Nell. Okay, now in doing this, you can see the recursive invocations by the indentation that I've put in. Now it wants to unify x1 with John, and you can see why that, because now it's matching on the colon colon. So it wants to unify x1 with John. And it wants to unify x with John. Somewhere it must have done some renaming, some substitution that wants it to do that. So
it's like recursively computing x1 with John and it substitutes x and
yeah, so and I don't exactly know what their setup is, but that's where it must be. That and now it goes on and wants to unify x2's with Mary, Nell. Well, that's the part where it has this one and this one. And that unification, it succeeds right away because you have a variable on the left and a term on the right. And that gives us enough that it now can say x is John as the answer because it got this ultimately out of here. And then it keeps on trucking in the same way. So the point that I wanted to make with this little exercise is that all Prolog does is it does unification. It then for the goals on the right hand side, it does them all in sequence, and whenever you have a choice point, it tries them all. And those are the things that you need to know about Prolog to understand what it does internally. And it's of course not super helpful to know that to solve an actual problem, right? When you have a homework assignment and say you're supposed to put in all the permutations, it's not really, the unification, goal stack, and choice points point of view doesn't really help you finding a solution. But when you are in the process of working out a solution, it sure is helpful to know that you ultimately have to be able to drive Prolog into this direction. It's also useful to understand when you have something where you get a stack overflow. We've had a case 2 lectures ago where if we had the goals in one direction, that you had a stack overflow, and then if you flipped the two, then everything was fine. And that is because of if you follow through how the backtracking works, then you can see why that would happen. And so knowing the computation model is helpful for that. All right, so do those homework assignments. They are not hard if you can think about them the right way. You can take a very long time with them if you don't think about them the right way. So, and if actually I find it more difficult with this one than with some of the other homeworks to understand the questions on Piazza. And to give good advice. But give it your best. Put questions on Piazza, and I'll try my best to decode them. You may at some points, if you have code that does something crazy, just put it on there, and at least we'll see crazy Prolog code. The other thing I noticed is that how singularly unhelpful Stack Overflow can be. So did any of you Google for something and find some Stack Overflow things? I found some of that where I said, that the answers there were not always the best. And that'll get even worse with the next homework. So this homework is just there for practice. The next homework, we will put Prolog to good use to solve some fun, at least I think, kind of fun puzzles. And as it happens, one of them has an answer on Stack Overflow that is so bad that I decided not to be deterred by that and to assign it anyway. All right, so let's hope that you all succeed with this, and we'll see each other on Monday.